All right, Chapter 5, List Comprehension. In this chapter, we introduce list comprehensions, which allow many functions on lists to be defined in simple manner. We start by explaining generators and guards, then introduce the function zip and the idea of string comprehension, and conclude by developing a program to crack the Caesar cipher. 5.1 Basic Concepts. In mathematics, the comprehension notation can be used to construct new sets from existing sets. For example, the comprehension x squared, where x is in the set 1 to 5, produces the set 1, 4, 9, 16, and 24 of all numbers x squared, such that x is an element of the set 1 up to 5. In Haskell, a similar comprehension notation can be used to construct new lists from existing lists. For example, x squared, where x is in 1 to 5, 1, 4, 9, 16, 25. Let's see. Nope. The symbol pipe is read as such that arrow from right to left is read as is drawn from, and the expression x is drawn from 1 to 5 is called a generator. A list comprehension can have more than one generator, with successive generators being separated by commas. For example, the list of all possible pairings of an element from the list 1, 2, 3, 4 with an element from the list 4, 5 can be produced as follows. So how do you read the whole thing? The pair xy such that x is drawn from the list 1, 2, 3 and y is drawn from 4, 5 is the list with those pairs. Changing the order of the two generators in this example produces the same set of pairs, but arranged in a different order. In particular, whereas in this case x, the components of the pairs change more frequently than the y components 1, 2, 3, 4, 1, 2, 3, 1, 2, 3, 1, 2, 3 versus 4, 4, 4, 5, 5, 5. In the previous case, the y component changes more frequently than the x component 4, 5, 4, 5, 4, 5 versus 1, 1, 2, 2, 3, 3. These behaviors can be understood by thinking of later generators as being more deeply nested, and hence changing the values of their variables more frequently than earlier generators. Later generators can also depend upon the values of variables from earlier generators. For example, the list of all possible ordered pairings of elements from the list 1 up to 3 can be produced as follows. The list of all possible ordered pairings of elements can be produced as follows. Okay. The list of all possible ordered pairings. As a more practical example of this idea, the library function concat that concatenates a list of lists can be defined by using one generator to select each list in turn, and another to select each element from each list. The wildcard pattern _ is sometimes useful in generators to discard certain elements from a list. For example, a function that selects all the first components from a list of pairs can be defined as follows. Similarly, the library function that calculates the length of a list can be defined by replacing each element by 1 and summing the resulting list. In this case, the generator, how do you pronounce that? The generator underscore drawn from x's simply serves as a counter to govern the production of the appropriate number of ones. 5.2 guards. List comprehensions can also use logical expressions called guards to filter the values produced by earlier generators. If a guard is true, then the current values are retained. If it is false, then they are discarded. For example, the comprehension x such that x is drawn from 1 to 10, even x, produces the list 2, 4, 6, 8, 10 of all even numbers from the list 1 to 10. Similarly, a function that maps a positive integer to its list of positive factors can be defined by factors is a function from int to a list of ints. Factor n is the list x, where list comprehension, where x is defined such that x is drawn from n up to n, and n mod x is 0. Similarly, a function that maps a positive integer to its list of positive factors. For example, factors of 15 is 1, 3, 5, 15. Factor 7 is 7. Recall that an integer greater than 1 is prime if its only positive factors are 1 and the number itself. Hence, by using factors, a simple function that decides if an integer is prime can be defined as follows. Prime is a function from int to bool. Prime n factors n is equal to 1 up and n. For example, prime 15 false, prime 7 true. Note that deciding that a number such as 15 is not prime does not require the function prime to produce all of its factors, because under lazy evaluation, the result false is returned as soon as any factor other than 1 or the number itself is produced, which for this example is given by the factor 3. Returning to list comprehension using prime, we can now define a function that produces the list of all prime numbers up to a given limit. Primes is a function from int to ints. Prime n x is defined such that x is drawn from 2 up to n prime, and x is prime. For example, primes of 40 is all the primes under 40. In chapter 15, we will present a more efficient program to generate prime numbers using the famous sieve of Eratosthenes, which has a particularly clear and concise implementation in Haskell using the idea of lazy evaluation. As a final example concerning guards, suppose that we represent a lookup table by a list of pairs of keys and values. As a final example concerning guards, suppose that we represent a lookup table by a list of pairs of keys and values. Then for any type of keys that supports equality, a function find that returns the list of all values that are associated with a given key in a table can be defined as follows. Find is a function from A that takes an A list of pairs of A's and B's, and returns a list of B's. Find key and then table, I suppose. Value where such that key prime V is defined such that it comes from T, and key is equal to key prime. For example, find B of A1, B2, C3, B4 is 2, 4. Wow, it's very elegant. 5.3, or maybe let's type that to see if it actually works. So find, let's put that on a new line. KT up V such that K prime V T oh, find B. I think, no, I can't copy. That's cool. The zip function. The library function zip produces a new list by pairing successive elements from two existing lists until either or both lists are exhausted. For example, zip ABC1234 is A1, B2, C3. The function zip is often useful when programming with list comprehensions. For example, suppose that we define a function that returns the list of all pairs of adjacent elements from a list as shown. For example, suppose that we define a function that returns the list of all pairs of adjacent elements from a list. I'll like group it into, okay, yeah. Pairs x's, zip x's with tail x's. What? How does that work? So, wait, so if we have x's is 1, 2, 3, then tail x's is 2, 3, and then if we zip that, don't we get 1, 2, 2, 3? Okay. 1, 2, 2, 3. Okay. Then, okay, yeah. Okay. It's different than what I thought it was. Okay. Then, using pairs, we can now define a function that decides if a list of elements of any ordered type is sorted by simply checking that all pairs of adjacent elements from the list are in correct order. Oh. True. Sorted 1, 2, 3, 4. Okay. Similarly, the function prime deciding that a list such as 1, 3, 2, 4 is not sorted may not require the function sorted to produce all pairs of adjacent elements, because the result false is returned as soon as any non-ordered pair is produced, which in this example is given by the pair 3, 2. Using zip, we can also define a function that returns a list of all positions at which a value occurs in a list by pairing each element with its position and selecting those positions at which the desired value occurs. Oops. Using zip, we can also at which value by pairing each element positions. Okay. Wow, that's quite elegant. Within the definition for positions, the expression 0 ... produces the list of indices 0, 1, 2, 3. This list is notationally infinite, but lazy evaluation only as many elements of the list as required. But under lazy evaluation, only as many elements of the list as required by the context in which it is used. In this case, zipping with the input list x's will actually be produced. Exploiting lazy evaluation in this manner avoids the need to explicitly produce a list of indices of the same length as the input list. 5.4 String comprehensions. Up to this point, we have viewed strings as a primary notion in Haskell. In fact, they are not primitive, but are constructed as a list of characters. For example, the string ABC string is just an abbreviation for the list of characters ABC car. List of characters, cares. Because strings are lists, any polymorphic function on lists can also be used with strings. For example, ABCDE, bang bang 2 is C. Take 3, ABCDE is ABC. Yeah, we get the picture. For the same reason, list comprehensions can also be used to define functions on strings, such as functions that return the number of lowercase letters and particular characters that occur in a string respectively. Okay. Count. Char string int. Okay. The Caesar cipher 5.5. We conclude this chapter. Oh, it's a short chapter, but a powerful one. With an extended programming example, consider the problem of encoding a string in order to disguise its contents. A well-known encoding method is the Caesar cipher, named after its use by Julius Caesar more than 2,000 years ago. To encode a string, Caesar simply replaced each letter in the string by the letter 3 places further down in the alphabet, wrapping around at the end of the alphabet. For example, the string Haskell is fun would be encoded as Gdinavoo LVXK. More generally, the specific shift factor of 3 used by Caesar can be replaced by any integer between 1 and 25, thereby giving 25 different ways of encoding a string. For example, with a shift factor of 10, the original string above would be encoded as follows: Rkukuvuv Skpex. In the remainder of this section, we show how Haskell can be used to implement the Caesar cipher, and how the cipher itself can easily be cracked by exploiting information about letter frequencies in English text. Encoding and decoding. We will use a number of standard functions on characters that are provided in a library data called data_char, which can be loaded into a Haskell script by including the following declaration at the start of the script. Import data_char. Oops. Parse error on. Oh yeah, okay, because we have those lists. Parse error on input. Oh, it has to be on top, maybe. Aha. And can we now do like, wow. Oh yeah. Okay, first simplicity. Oh yeah, at the start of the script, I need to learn to read. For simplicity, we will only encode the lowercase letters within a string, leaving other characters such as uppercase letters and punctuation unchanged. We begin by defining a function let_to_int that converts a lowercase letter between A and Z into the corresponding integer between 0 and 25, together with a function int_to_let that performs the opposite conversion. Oh. Okay. Plus n, n, okay. And cur, how, that's kind of ugly. You need to know that cur is a cast. I mean, it's a function from characters to, I suppose this is Unicode. The library functions ord and cur convert characters and their Unicode numbers. Okay. For example, let_to_int of A is 0, let_to_int_to_let of 0 is A. Using these two functions, we can define a function shift that applies a shift factor to a lowercase letter by converting the letter into the corresponding integer, adding on the shift factor and taking the remainder when divided by 26, thereby wrapping around at the end of the alphabet and converting the resulting integer into a lowercase letter. Okay. Oh, he put a... This should be on a new line. Let's try that. Then we need to have those others. Yep. Oops. Okay. Let to int of a let to int to let. What was let again? Letter. Okay. Int to let of 0. Okay. And then we can define shift. Oh yeah, shift NC is lower. Is that built in or? Okay, that's a built-in function. This is probably in data care. Is lower C into let to int C plus n mod 26. And I forgot a brace somewhere. A parenthesis, I mean. Otherwise is C. Shift 3A. Okay. I wonder, in Haskell you can do like an exclamation to say first evaluate the stuff behind. I think it's with the exclamation mark. I'm not sure, but then you don't need to write all these parentheses. Like I think we can write it like oh no. Oh no. Like this. Oh no. Okay. I swear there is a way to do that, but using shift within a list comprehension, it is now easy to define a function that encodes a string using a given shift factor. Encode int string encode n x's shift n x from x's. So haven't we learned map yet, or is this better than map or something? A separate function to encode a string is not required, because this can be achieved by simply using a negative shift factor. For example, encode 3 Haskell is fun is kdvdnu lv xku. Encode negative 3 of kdvdnu lv xku is Haskell is fun. Very cool. Frequency tables. The key to cracking the Caesar cipher is the observation that some letters are used more frequently than other letters in English text. By analyzing a large volume of such text, one can derive the following table of approximate percentage frequencies of the 26 letters of the alphabet. Table. Okay, for example, letter E occurs most often with a frequency of 12.7. A, B, C, D, E. While Q and Z occur least often, within a frequency of just 0.1%. It is also useful to produce frequency tables for individual strings. To this end, we first define a function that calculates the percentage of one integer with respect to another, returning the result as a floating point number. Okay. We first define a function that calculates the percentage of one of the. Okay. Okay. Simple function, yeah. Into float converts an integer into a floating point number. You would think. Didn't we learn that this one? Because there's div, which throws away the. Wait, let's see. Because. Wait. Yeah, because that thing only works on. Don't you have this thing? No. Maybe that's from Python or something. Oops. Okay. Using percent within a list comprehension together with the functions lower and count from the previous section, we can now define a function that returns a frequency table for any given string. Percent count. We did. Did he write count before? I think he did, yeah. Okay, count. Percent. Okay. Okay. I thought he was gonna do it with words now, no? Why did he? To this end, blah, blah, blah. Okay, no, Yeah, okay. Cracking the cipher. A standard method for comparing a list of observed frequencies, OS, with a list of expected frequency, ES, is the chi-square statistic, defined by the following summation, in which n denotes the length of two lists and x's I denotes the ith element of a list x's counting from 0. Okay. The details of the chi-square statistic need not concern us here. Only the fact that the smaller the value it produces, the better the match between the two frequency lists. Using the library function zip and a comprehension, it is easy to translate the above formula into a function definition. Chi-squared, float. Okay. Man, this is why does he? Yeah, okay. In turn, we define a function that rotates the elements of a list n places to the left, wrapping around at the start of the list, and assuming that the integer argument n is between 0 and the length of the list. Okay, so he's gonna Yeah, I think I kind of see where he's going. Now suppose that we are given an encoded string, but not the shift factor that was used to encode it, and wish to determine this number in order that we can decode the string. This can usually be achieved by producing the frequency table from the encoded string, calculating the chi-square statistic for each possible rotation of this table with respect to the table of expected frequencies, and using the position of the minimum chi-square value as the shift factor. For example, if we let table prime frex of Kedivenu live xker, then chi-square rotate n table for n from 0 to 25 gives the result this, in which the minimum value 202.42 appears at position 3 in the list. Hence, we conclude that that 3 is the most likely shift factor that was used to encode this string. Using the function position from earlier in this chapter, this procedure can be implemented as follows. Crack. Using the function positions from earlier. The function position. Is this the name of a function? Positions. It gives the positions. Okay, positions. Using the function positions from earlier in this chapter, this procedure can be implemented as follows. Crack from string to string, crack x's, encode negative factor x's. What is factor again? Is that a function? Maybe I should make a habit of typing everything that he defines, so that I can just quickly check the code. Factors. Okay, yeah. The prime factors. Or just the factors. But why does he... no, factor. Where factor. Oh my god. This where syntax is just annoying. Okay, where factor is head positions minimum chi tab. Whew. More generally, I don't really understand. Okay, more generally, the crack function can decode most strings produced using the Caesar cipher. Note, however, that it may not be successful if this string is short or has an unusual distribution of letters. For example, crack encode 3 Haskell Pieter-Jan. More generally, the crack function can decode most strings produced using the Caesar cipher. Note, however, that it may not be successful if the string is short or has an unusual distribution of letters. Crack 3, boxing wizards jump quickly. Okay. 5.6, chapter remarks. The term comprehension comes from the axiom of comprehension in set theory, which makes precise the idea of constructing a set by selecting all values that satisfy a particular property. A formal meaning for list comprehensions by translation using more primitive features of the language is given in the Haskell report. Hall. A popular account of the Caesar cipher and many other famous cryptographic protocols is given in the codebook. Yeah. Um, mm, 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 mm. My internet is slow. Oh no. There's a famous programming book called Code. I haven't read it, but oh no, you can see my location. Okay. A popular account of the Caesar cipher, blah blah blah. Exercises. Okay. I think maybe I'm going to do these exercises later because I'm tired. Using a list comprehension, give an expression that calculates the sum 1 squared plus 2 squared for the first 100 integer squares. Okay, that can't be that hard. Sum of x such that, x squared such that x is taken from 1 up to 100. Boom. Okay. See you another time.